Okay, everyone, I'm going to go over what Bode plots are today. So, Bode plots are a great way to visually represent the gain and phase of a system. The phase and gain of a system. And then the way they do it is using a logarithmic scale. And then it uses the transfer function. We use the transfer function to plot the Bode plot. And so for the transfer function, we kind of want it in a specific shape. So for our transfer functions, what we kind of see is like a k, which will be a constant, and then you'll have a j omega, and it will be a plus or minus n. The plus or minus just indicates it could be on the numerator or the denominator. And then you have a 1 plus j omega divided by z, and then that could also have a power to the n, and that z is just basically saying the location of zeros. And then you can have a quadratic, so it will be 1 plus j2 zeta omega divided by omega k, omega k plus j omega divided by omega k squared. And so we can basically have the same thing in the denominator as well. And then in this case, it won't be a z on the denominator, it will be a p for the pole location. And so essentially, this is the general shape of transfer functions that we will see, or we need to turn the transfer function into, so we can plot the Bode plots. So in order to get the magnitude, what we do is from the transfer function, we take the 20 log of the item. So it would be 20 log of base 10 of the magnitude of the transfer function. And so, for example, if we're doing this, if we have a example where the transfer function is 1 plus j omega over z1, to get that for the HDB, so what we do is HDB equals the 20 log of base 10 of the magnitude of that transfer function, so it would be 1 plus j omega divided by z1. So when you do that, you want to think about it in like a steady state or at time equals 0. So if you have HDB at time equals 0, what you get is 20 log of base 10 of 1 plus 0. And so log of 1 is going to be 0. So therefore it's going to be 20 times 0, which gives us 0. So, but then if you do HDB of infinity, we get 20 log base 10 of 1 plus infinity. So since log is a continuous function and ever increasing function, it's going to be 20 times infinity. So therefore it's going to be infinity. So, and then to do the phase, if we wanted to do the phase of this, what we would do is we would take the inverse tangent of that factor. So let me write this. Phase equals inverse tangent of omega divided by z1. And so when you think about it, if you look at three cases, when omega equals 0, when omega equals z1, and omega equals infinity, as you get closer to 0, you for omega, you get 0, but then as you get closer to infinity, you get 90. And then right in the middle, when it is z1, you get 45 degrees. So we're gonna try plotting this, but we're gonna assume I'm just gonna make the assumption just to make our plots look nice. Z1 equals 1. So we're gonna draw this out. Okay, so we have HDB, and since this is a logarithmic scale and not a linear scale, what we will have is 0.01, 0.11, and then 10. So for this case, like we said before, it's going to be 0 and then 0 as you get closer to infinity, and then as you get it's going to be 0 as you get closer to 0, and then as it's going to be infinity as omega gets closer to infinity. So what the shape of the graph would be is it's going to be 0 up until it hits that 1 where that 0 was, and then it'll start increasing. So let me just draw this point right there, and it'll just keep increasing like that, and that's going to be a 20 dB per decade slope. And when we draw Bode plots, you want to indicate the slope, because sometimes it might be 40, 60, even 80. So you just want to know what the slope is. And then just make that point right there, 20. So for the phase, what happens is at Z1, like before, Z1 where Z1 is equal to 1, so at omega equals 1, it's going to be 45. So omega equals 1, it's going to be around 45. And then so basically when it's 1/10 of the pole or 0 location, it starts increasing. And then when it's 10 times that pole location, it levels out at 90. So it'll basically be 0 for all this period, and then it'll be 90 at this point right there, and then it's just gonna connect right there. And so that would be the phase of the system right there, and then that would be the magnitude. So that would be the Bode plots for both of these, and then it's omega down there. Okay. So now each case, so I looked at when it was this part right there. That's what I focused on. But remember how at the top you could have either this, you could have this, or this, and each case has its own phase and magnitude plot. So I don't want to go through the derivations of all that. So that's why, and if you go to table 14.3 or what page was it? 621. It shows you all the elements of that in general formula, like this one right here. It'll show you what the phase and magnitude of this, and all these individual things. So you can just look at that and kind of go over that.